Like the term plastic, toughness is a term that has a particular meaning to us in engineering when we talk about materials as compared to our everyday vernacular. And so a lot of times it'll be confused with strength. But strength is associated with stress. The maximum amount of stress that a material can endure is the yield strength. But toughness is a little bit different. So if we take a diamond, for example, a diamond is very strong. It has a very high yield stress, but it would not be considered very tough. It can be suggested to great force and then return to its original shape, but once you exceed that maximum force, it's subject to shattering. It'll just obliterate. On the other hand, polycarbonate, we would never think of the material that's used in like a helmet or a bumper or something like that as being very strong. It's going to be pretty easy to dent and to permanently deform, but it can absorb a great deal of energy per unit of mass, so we would say that it is very tough. So toughness, as measured on a stress-strain curve, is the area underneath the stress-strain graph. So in the case of something like a diamond, this would be something along the lines of what we see here in the orange. So in this case, we see a much higher yield stress, but there isn't a whole lot of space for deformation, plastic deformation that comes after it. And instead, you end up with this brittle fracture, kind of like what was mentioned about a diamond. On the other hand, if you take a material like a polycarbonate, you're going to see something more along the green line. So you have a much lower yield stress, so it's going to enter into permanent deformation much sooner, but you can have a much longer period of time where the material can still support the stress that's being applied to it and not completely fail, tear apart, or shatter. And so it simply depends on what purpose the material is going to be used for, whether you need a lower yield stress but a more tough material versus something that has a very high yield stress that you probably won't approach, and so therefore fracture isn't a concern. So to calculate toughness, we're going to, again, find the area underneath the stress-strain curve. So that means we're just multiplying stress times strain to find that value, to find the toughness. Now, we do know that strain is a dimensionless quantity, but it's going to be in our interest to include the length over length as part of our analysis of the units to see what units we end up with for toughness. So newtons per meter squared is our stress. Strain is length over length, so that's going to be meters over meters. So if I multiply those, instead of canceling out the meters, I'm going to get Newton meters on the top and then cubic meters on the bottom. So hopefully we recognize Newton meters as being an energy unit, joules, and then we've got joules over meters cubed, so joules per unit of volume, so energy per unit of volume is the measure of toughness. So again, toughness is the calculation of how much energy a material can absorb per unit of volume. And so the typical way that a material will be tested in a laboratory to determine what its toughness is, it's usually an experiment along the lines of when the material is struck by a heavy hammer of some sort to determine the exact amount of stress that's applied, measure the strain, and then therefore calculate the toughness. So in the example we have here, we've seen this graph before. It's a stress-strain curve for an idealized steel. So we've got a yield strain here of 0.15%, and then we've got the fracture strain is here at 1%, and then we have a yield stress at 200 megapascals. So again, the area underneath the curve is going to be our toughness for this material. But there's two different types of toughness. There's the elastic toughness, which is going to be the area underneath the curve that's just in the triangle there. And so that's the amount of energy that the material can absorb and still rebound back to its original state. So to calculate that, we're going to find the area of that triangle. So we're going to have 1/2 times, now we've got the strain there is 0.15%. So we'll convert that to a decimal at 0.0015. And even though strain is dimensionless, we are going to include that meters over meters to make sure that it matches up units-wise to result in that joules per meter cubed that we want in the end. Then I'm going to multiply that times the stress, which is that 200 megapascals, but we should convert that into a number that we can work with. We don't just want to leave it as 200. So 2.00 times 10 to the 8th, and instead of pascals, I'm going to put newtons per meter squared. So we're multiplying those to find the area underneath the curve. We can see we're going to end up with our newton meters in the top, so joules over meters cubed on the bottom. So if we multiply that out, we end up with 1.50 times 10 to the 5th joules per meter cubed. So that's our elastic toughness, 150,000 joules per meter cubed. Now, we do want to follow the convention of reporting our answer as a number between 1 and 999 by adjusting the units with the appropriate prefix. So if we have 150,000, we're going to move the decimal 3 places. So instead of giving this answer as 150,000 joules per meter cubed, we'll report this answer as 150 kilojoules per meter cubed. So our rule throughout this unit is going to be to adjust our answer so it is in this 1 to 999 range by reporting it with the appropriate prefix in front of our answer. Now the other type of toughness that we need to calculate is the plastic toughness. And so now this is the total amount of energy that the material can absorb before it doesn't just get deformed, but it actually fractures and breaks. So for that, we need the area underneath the entire curve, triangle and this rectangular region included. So we can treat it as a trapezoid, so we can find it all in one calculation, or we can take what we've already done. So we've got the 150,000, and I'm going to leave it as 150,000 here, joules per meter cubed, and then add together the area of this green rectangular region that we have in the graph. So again, the height of our triangle is going to be, or rectangle, is going to be this same 200 megapascals. So we're going to have 2.00 times 10 to the 8th newtons per meter squared. And then we're going to multiply that by the base of our rectangle, but we don't want to fall into the trap of using 1% as the base. But because remember we're cutting off this part of the base here that was part of the triangle, so we've got 1% minus 0.15%, which is 0.85%, or if we convert it into a decimal, 0.0085 meters over meters. Again, using that convention to make sure that our dimensions work. So for this part here, if we multiply that out, we're going to end up with, so we first have our 150,000 joules per meter cubed plus multiplying 200 million times that 0.0085, we end up with 1,700,000 joules per meter cubed. So now if we add these together, we're going to end up with 1,850,000 joules per meter cubed. But again, we don't want to leave our answer in this format. We want to reduce it down so it is somewhere between 1 and 999. So that means I'm going to move the decimal not just 3 places in this case, but 6 places to get an answer of 1.85. And then since we've moved the decimal 6 places, it's not going to be kilojoules per meter cubed, but times 10 to the 6th is megajoules. So it's going to be megajoules per meter cubed. So we've got the elastic toughness, the amount of energy that the material can absorb before it is permanently deformed is going to be this 150 kilojoules per cubic meter. And then the total amount of energy it can absorb before it fails, breaks, shatters, etc. The plastic toughness is this 1.85 times megajoules per meter cubed.